Welcome, Math 3380 students, to the second quick review video that we have today. And in our last video, we talked about Greek fractions and reminding ourselves of some of the oddities about the way in which they were able to notate fractions. And in this next part, I want to come back and talk about Babylonian fractions, because there were a couple of things that got missed out there. And one of those things had to do with sort of comparing what we know from our work in base 10 and being able to sort of translate or transfer that into a situation where we were thinking in base 60. So in particular, one of the things we know in base 10 is that when we work in base 10 and we have small bits and pieces and parts, we talk about having what are called decimals, or sometimes we even call them decimal fractions. And in the same way, what we want to do is we want to talk about those kinds of pieces and parts that we can have, but we're not in base 10, so we can't call them decimals, so we're going to call them sexagecimals. And this was a word that came along as we learned about our work in base 60. Now, when we think about what we know from base 10, when we talk about decimals, there were two types of decimals that we can have: those that terminate and those that repeat. And by that, in base 10, we mean a terminating decimal might be something like 1 75/100ths. We know that terminates because there are no further digits to the right of the decimal point, or what we would use as our separatrix. And in our repeating decimal, we could have something like 7 repeating, and we would know that that continues on, or we even learn how to write that using a bar over the 7 to indicate that we're going to have that sort of repeating situation. Now, just as we have with decimals that they're terminating and repeating, we're going to have the same thing with sexagecimals. And so again, we want to work on making sure we can translate what we do in a base 10 situation to what we're doing in a base 60 situation. Let's just take a decimal situation. And so we're going to use this as a decimal example. And we're going to talk about there being a non-terminating decimal representation that we want to look at. So let's just use what we were talking about a minute ago. Suppose we have the non-terminating decimal where we have a 7 in every single place to the right of the decimal point. So we know if we were to think about that, that would be, as we said, without using that notation, just a string of 7s that are going on infinitely. Now, another way that we can think of this is to think of it as a sum. So as we look at something like this, we can see that that 7 right there is in the 10ths place. So we can talk about there being 7/10. And then if we go forward, we can say, well, there's another 7 there, but it's not in the 10ths place, it's in the 100ths place. So we can talk about 7/100ths. And then we can talk about the next place over. And we know that when we think about that one, it's still going to have a numerator of 7, but the denominator is going to be the next power of 10 because we're working in a base 10 system. And we know that this is going to continue as we go forward. Now, if we want to know, if we want to switch from what we're talking about in terms of a decimal, we wanted to rewrite this as a fraction. What we really need to do is we need to be able to sum together 7/10 plus 7/100 plus 7,000 plus etc. And one of the things that we can notice here is that as we're moving from add-end to add-end along this strip, we keep multiplying by a factor of 1/10. And if we're going to go to the next one, we would be multiplying by a 1/10. So we're multiplying by what we call a common ratio. So the common ratio for this decimal, for this series that we've set up, typically called R, is going to be equal to 1/10, because that's what's happening as we move from term to term. It's a multiplicative relationship. And when we have that kind of a relationship, when we think about this sum that we're trying to find, 7/10 plus 7/100 plus 7,000 and so forth, we see this as a geometric series. And for those of you in calculus, you've encountered this idea of series. And for those of you that are going to be in calculus next semester, this is an idea that's going to come back and you're going to get some more exposure to it. But one of the things that we learn as we look at this situation where things are multiplicatively related and we have this what's called a common ratio, that we have all the information we need to figure out how much or what the sum of this would be. Because we know that the common ratio is 1/10, and we also know that the very first term of the sequence of this of the series is the term 7/10. So I know where to start my series, and I know how to multiplicatively grow it. And it turns out that if we know those two things, then we can find the sum very easily, because we're just going to take the first term and we're going to divide it by 1 minus the common ratio. So in this particular example, our first term was the fraction 7/10. And our ratio was 1/10. So if we do a little bit of arithmetic, we're going to have a numerator of 7/10, and we're going to want to divide that. Well, if I remove 1/10, is going to leave me with what? 9/10. And then I remember, how do I divide fractions? Well, this is just going to be 7/10 times 10/9. The beauty of this is that my factors of 10 in the numerator and denominator are going to disappear. And what's going to happen is that I'm going to end up with a numerator of 7 and a denominator of 9. And my claim is that this represents the fraction that represents this decimal of 0.7 repeating. So you can try that. Get out your calculator, take 7 divided by 9. Is this the decimal representation that you get back? And you're going to find that it is. All right, so let's think about a non-terminating sexagesimal. That would look very similar to what we had, but of course our separatrix is different. The base is different. So for example, I could have a non-terminating sexagesimal that looks like this. And I can see that this pattern is going to continue in that way. So again, it looks different slightly just because we're in a different base, but the thinking about this is going to be exactly the same. What I want to do is I want to know, what would this look like in our everyday fraction form? Right now it looks like a repeating sexagesimal, but what would it look like in fraction form? We're going to want to sort of check that out and see what's going on there. Well, let's do the same thing that we did before. If we understand that this is base 60, then one of the things that we can notice is that this would be in the 1/60th spot. This would be in the 160 squared spot. This one would be in the 1/60 to the third spot. And this would continue on in that same fashion, just like it's 1/10, 1/100th, 1/1000th, if the base were 10 instead of 60. That change is always going to be by a factor of 1/60th. Now, if we were to write this in our expanded form, sort of in our geometric series form, would you agree that this would look like 23/60 plus 23/60 squareds plus 23/60 to the thirds plus 23/60 to the fourth, etc., right? So here's my geometric series. Now there were two things that we said were important in establishing a geometric series. One was, can you tell what the common ratio was? And the second thing was, do we know where we're going to start? What's the first term of the series? Well, we certainly know what the first term of the series is. It's 23/60. Do we know what the common ratio is? Well, as I move from here to here, I'm multiplying by a factor of 1/60. Just like before, I was multiplying by a factor of 1/10. So every time I move from the first term to the second, or the second to the third, and so on, every time I'm multiplying by the same amount. That means this is a multiplicative relationship. We have a common ratio, and that common ratio is going to be 1/60. So here's the information that I need, because this is just another geometric series. We don't care in a geometric series whether the base is 10s or 60s or 23s or 52s or 1000s. We don't care what that is. What we want to do is we want to think about what the sum of this would be, so that we can determine what that fraction is that led to this sexagesimal, this non-ending sexagesimal. So we said before that we were going to take the first term over 1 minus the common ratio. So in terms of this example, our first term is 23/60, and we're going to want to divide that by 1 minus 1/60. So we have that 1/60. So let's see, in reality then, we've got what? 23/60 over, well, 1, if I remove 1/60, would be 59/60. So that's what? 23/60 times the reciprocal 60/59. And again, nice and handy here that our factors of 60 in the numerator and denominator are going to disappear. So my simplified version of this fraction is going to be what? 23/59. So my claim is that if I start with the fraction 23/59, that's my fraction, that if I then tried to put it into sexagesimal form, I should see that the quantity of 23/59 is the same as my quantity of 23 repeating in terms of what's there. So this is going to be my final answer. So a non-terminating sexagesimal, we're going to use what we know from our world of base 10 and from our previous experiences to kind of help us with that particular idea. So this was one of the areas where there was difficulty, and students maybe chose not to engage with this. But I encourage you to go back to your notes from this section on Babylonian fractions. You can find that in the Unit 2 area. And you will find you may have your original notes, and this may have helped clarify what's going on there. But for certain, make sure you've taken some notes so that you're ready to handle any questions that might be like this on your module quiz.